Alright, it's Niaki. It's Niaki Osteozone. So today we are going to have a chemistry revision from the June 2025 paper, the paper which was written from the ZIMSEC exam board. So here we don't mainly focus on exam board. So our chemistry is still the same regardless of the exam board, right? So sodium doesn't change with the exam board, right? So sodium will remain the same, right? So we are now moving on to number 6. So number 6 says, in the electrolysis of acidified water, oxygen and hydrogen are produced. In the electrolysis of acidified water, oxygen and hydrogen are produced, right? So we did this in our topic or tutorials, so you need to check on our playlist, right? So we said water is being acidified. Why? Because water doesn't conduct electricity, right? It doesn't have a free mobile ion or free mobile electrons to conduct electric current. So we are acidifying it so that we can increase its conductivity, so that we can ionize water, right? So we are going to have oxygen and hydrogen being produced. So we are having this equation, 2 moles of water giving 2 moles of hydrogen plus 1 mole of oxygen. So this is the equation, right? And then the first part says calculate the volume of hydrogen produced if you are to produce 50 cubic centimeters of oxygen at RTP, right? So as you can see from this equation, oxygen and hydrogen, they are produced in the ratio 2:1, right? So from the equation, we are having 1 mole of oxygen, and then which corresponds to 2 moles of hydrogen, right? So since the volumes are proportional to the moles, so we have what you call the Avogadro's law. The volume is proportional to the number of moles. So for all level, we don't allude much on the Avogadro's law, right? So 2 moles is equal to 1. So we are simply going to say the volume of hydrogen is twice that one of oxygen, right? So it's 2 by 50 to give us 100 cubic centimeters, and we are done. As simple as that. And then we go on to the next part of the equation, which says explain why the method of electrolysis is an expensive method of producing oxygen. So this method is not quite of industrial use. Why? Because it is very, very expensive. The cost of electricity is very, very. The cost of electricity is very expensive, right? So this will make it less economical for large scale production of oxygen. Are we together? But we can use other methods like fractional distillation. We can use fractional distillation. Are we together? And then we go on to the next part. So let me clear so that we can easily see. Alright, so the next equation says hydrogen is used in the production of copper from copper to oxide, according to this chemical equation. So here is the chemical equation. So from this chemical equation, you can deduce that this one is what we call a displacement reaction. A displacement. So we did the reactivity series, and then we can deduce that from the reactivity series that hydrogen is more reactive than copper, right? So hydrogen can reduce copper. It can displace copper from its components. So here copper has been displaced, and then hydrogen has been oxidized, right? Oxidation defined by the gaining of oxygen, reduction defined by the loss of oxygen. Are we together? So the question says calculate. So here don't only focus on the given question, but we try to expand the question so that we can understand any concept within that given radius, right? So calculate the volume of hydrogen required at RTP to produce 1.6 grams of copper, right? So we want to produce 1.6 grams of copper. So from this equation, 1 mole of hydrogen will give 1 mole of copper, which is equal to 64 grams. So stoichiometry is all about comparing. It's all about comparing the ratios using the stoichiometric ratios. So 1 mole here. So the volume at RTP, right? So volume of 1 mole at RTP is equal to 28 cubic decimeters. So this volume differs with the example, right? So this volume differs with the example. So for Cambridge it's 24, but for ZIMSEC it's 28. So you need to stick to your example here, right? You need to stick to your example. So the purpose of these discussions is for you to have the understanding, not cramming papers, right? So you need to stick to examples here. And then so we are saying 28 is equal to 64 grams. 28 cubic decimeters is equal to 68 grams. So what volume do we need to have for us to produce 1.6 grams? So less will give us 1.6 grams. So we are simply applying. So it's 1.6 over 64 grams multiplied by 28 cubic decimeters. This one will cancel with this one, and then we are going straight to our calculator. So it's 28 by 1.6 divided by 64, and then we are going to have 0.7 cubic decimeters, and we are done, right? And then we move on to the next part, which says state and explain the role of hydrogen in this equation. So we said hydrogen is a reducing agent, right? So hydrogen will reduce copper oxide to copper metal. So this is the role of hydrogen. It is a reducing agent. So you should be able to define the term reducing agent and to define oxidizing agent, and also to give the examples. So reducing agent, mainly we have metals, right, arranged with their reducing ability from the reactivity series, right? So the one at the top of the reactivity series, they've got a higher reducing power. And then oxidizing agent. So for oxidizing agent, we have the halogens, the group 7 elements, right? And then we have the manganese, we have potassium dichromate, potassium permanganate, and etc., right? So the role, it is a reducing agent. And then how does it reduce? So a reducing agent, it is one which is being oxidized after the reaction. The one oxidized after the reaction. And then oxidizing agent, the one reduced after the reaction. So an oxidizing agent is the one which is reduced after the reaction. A reducing agent, it is the one oxidized after the reaction. Are we together? So here hydrogen, after the reaction, it is oxidized. That's why we said it is a reducing agent. So you must understand this, right? And then we go on to the next part. So the next part says water samples from sources A and sources B were analyzed, and then water source A and then water source B, and then the test, and then we are heating for minutes, and then heated for minutes, and then observation, we are going to observe a white precipitate for A, and then no observable change for B. All right, so here we are using water, right? We are using water. So this is hard water. So we have permanent hard water, and then we have temporary hard water. So you should have the understanding of this, right? So for permanent, we are having salts like calcium sulfate, and then for temporary, we have the hydrogen carbonates, right? So you should understand this. And then on heating, hydrogen carbonates will decompose to form the carbonates, right? We decompose to form the carbonates. And then from the understanding we have from acids, bases, and salts, we learned that all the carbonates are insoluble, except those one from group 1 and ammonium. These are the only soluble carbonates, and then all the other carbonates are insoluble, so they are going to give the white precipitate. So we are going to have calcium carbonate, we are going to have the group 2 carbonates, right? So they are going to give this white precipitate. Are we together? And then here we are going to have for permanent hard water, we are not going to have any carbonates, right? So no observable change. Are we together? And then state suggesting explanation for the difference. So we have explained the difference, right? And then state any 2 advantages of drinking water source from A. So water source from A contains a lot of minerals. So it contains a lot of minerals. So we're going to have magnesium and calcium ions, which are essential for the bone formation and teeth formation. So which are essential for bone formation and then teeth formation. Are we together, guys? So we go on, we proceed to the next part. So number 7 says the electronic configuration of an element Y. This is the electronic configuration. So when we did the electronic configuration in our topical series, we said from the electronic configuration we can deduce the group number. So this number in the outermost shell is the group number. The number of electrons in the outermost shell denotes the group number. So this element is in group 2. We can also deduce the number of shells. So this number of shells, you're going to have 3 shells. So the number of shells is equal to the period number. Are we together? The number of shells is equal to the period number. The number of electrons in the outermost shell is equal to the group number. It's simple as that. And we also said group 1 to group 3 are the metals, and then the metals they react by losing electrons, and then the non-metals are from group 5 to group 7, they react by gaining electrons or by sharing. And then group 4, we have an anomaly. We are starting with carbon, and then silicon, and then germanium, and then tin, and lastly we have lead. And then we have an increment in the metallic nature as you go down the group. This one is the only non-metal, these 2 are the semi-metals or the met, and then lastly these 2 are the metals. And then group 8 are chemically inert, they exist as monoatomic structures. So you need to take note on that, right? And then group 8 is the stable noble gases. All elements they react, they want to have the same electronic configuration like the stable noble gases. So this is what you need to know for the atomic structures. As simple as that. And then the question says, give the molecular formula of the compound formed when Y reacts with chlorine. So we said Y is a group 2 element, it will form the ion, this divalent ion, right? And then chlorine is a group 7 element, it will react to gain 1 electron. And then we said we are going to exchange the coefficients of the charges. So the 1 here goes there, and then this 2 will go there, right? So we are going to have this. As simple as that. So we can ignore the 1 by saying, so you can take in group 1, in group 2 element, magnesium chloride. As simple as that, right? And then the question says, explain why the compound formed when Y reacts with chlorine, conducts electricity when in molten, is a high boiling point, is soluble in water. So we are being required to give the properties of ionic compounds. So we have a series on this. So if you follow our playlist, our topical playlist, this is going to be very, very easy for you. Why? Because we discussed this, right? So we know the trend of the equations. So pay very special attention to the playlist, the topical playlist, and then these papers will be a walkover for you. So conduction of electricity, we said conduction is only done in the molten and in the liquid or a solution or aqueous form, right? Not in the solid. And we explained in the solid we doesn't have free mobile ions to conduct the electric current. So conduction in ionic compounds, it is done by ions, not by electrons, right? So here we have free ions are mobile, they are able to move to conduct the electric current. And then for high boiling point, we explained that boiling point is governed by the forces yielding the particles within the lattice structure, the forces. So if we are told that a particle or a substance, a chemical substance, has got a high melting point, it simply means to say this the forces yielding the particles in the lattice structure, they are strong. That's why we are requiring a high temperatures. That's why we are having a high boiling point. So here we are having stronger forces, stronger ionic forces, electrostatic forces of attraction between the oppositely charged ion, the cation and the anion. And then for the solubility, we explained solvation. So for all level, we don't normally explain the solubility, but for the sake of understanding, I want to illustrate using this water molecule. So we have what you call electronegativity and electropositivity. So we don't normally want to explain these terms for you guys because it's quite complicated for you, but I want to just to illustrate so that you can comprehend, right? So we have oxygen. So oxygen has got 2 lone pairs of electrons here after the bonding. Lone pairs, these are electrons which are not included in the bond, right? Electrons which are not in the bonds, and then these are called bonding pairs, electrons within the bonds, right? So these lone pairs can attract. So let's take sodium chloride as an example. We have the sodium ion and then we have the chloride ion. So this sodium ion is going to be attracted to this negative center. Unlike charge is attracted, this is the negative region, this is the positive region. So this sodium will be attracted to this negative center, and then this chloride ion, which is a negative, will be attracted to this hydrogen ion. So this will result in this splitting of this sodium chloride molecule compound, I mean. So water will infiltrate between the particles, thereby splitting this sodium chloride. Hence the particle will dissolve. So this is how ionic compounds will dissolve in water. I think I have tried to explain I've tried to break it down for you so that you can clearly figure out what's happening, right? So we are on number B. So number B says fig 7.1 shows the flowchart for the production of sulfuric acid. So we are having sulfur dioxide, we are having oxygen from air, and these are the conditions for the contact process. So this one is the contact process. So we have discussed the industrial processes in our video tutorial for all the industrial processes. And then we are having sulfur trioxide, oleum, and then concentrated sulfuric acid, right? So we can write this one in this equation, right? Plus oxygen. So this one is a reversible reaction, meaning to say it is a reaction which proceeds in either directions. So we are having, these are the conditions for the reaction, and also the reaction is an exothermic reaction, right? So we want to understand, we want to explain how these conditions affect the yield of sulfur trioxide. So for industrial processes, our main agenda is to increase the yield, and also to cut or to reduce the costs, right? So we want to compromise the conditions so that we can increase the yield and thereby and also compromise the cost, right? So here this one is an exothermic reaction, meaning to say we need to have, to favor the production of sulfur trioxide, we need to have reduced temperature, we need to have lower temperatures so that the equilibrium position will shift to the products to the right. And then we need also to have higher pressure so that the equilibrium position will shift to the direction where we are having a fewer number of moles. So but here we are having a temperature of 450, but we said we need a low temperature. So we are using a compromised temperature. Why? Because we want to favor the forward reaction and also making the reaction faster. That's why we used a compromised temperature. So first, for you to answer this question, you need to highlight that according to Le Chatelier's principle, we must use low temperature to favor the exothermic direction. But we used a compromised temperature of 450 so that we can have a faster reaction, right? And then why is sulfur trioxide not directly dissolved in water? Why? Because it will form fumes of sulfuric acid which are difficult to condense, right? It is going to form fumes which are difficult to condense. And then a pressure of 1 atm is used. So we said we want to use high pressure here, high pressure and then low temperature. So we want to use high pressure according to say Le Chatelier's principle. So you should know the Le Chatelier's principle by heart, right? So the Le Chatelier's principle requires us to use a high pressure, but we used a pressure of 1 atm. So why do we use this low pressure? We use a compromised pressure because high pressures are difficult. High pressures are difficult to maintain and are also expensive to maintain. Are difficult and expensive to maintain. That's why we use the compromised pressure. So you should understand the Le Chatelier's principle. You should know this Le Chatelier's principle by heart. So the Le Chatelier's principle says, let me highlight the Le Chatelier's principle. So the Le Chatelier's principle says when a system in equilibrium is disturbed, the equilibrium position will shift in a direction that will counteract the change. Right? So this is the Le Chatelier's principle. It is the one which governs all these reversible reactions, right? And then we now move on to the next part. So give any two advantages and any two disadvantages of using herbs in agriculture. So we can say that herbs, they're environmentally friendly and biodegradable. Environmentally friendly and then biodegradable, and then they are cheaper, right? And then the disadvantages, some says they are less effective than synthetic chemicals or pesticides, synthetic pesticides. And also they may require frequent application. They may require frequent application, right? Are we together? And then the other question says, outline any 3 environmental problems associated with the manufacturing of sulfuric acid. Outline any 3 industrial problems. So we are going to have the emission of sulfur. So you can say the emission of sulfur dioxide, which is acidic. So sulfur dioxide is an acidic gas, right? So it can cause acid rain, right? We can also have the discharging of acid rain or acidic water, acidic waste water in the water bodies, polluting the water bodies. So this will affect the aquatic environment, right? So the sources of sulfur, we can extract sulfur from iron pyrite. So this will result in the solid waste, which can contain heavy metals, containing heavy metals. Are we together? So this is what you need to know for number 7. And then we are now moving on to number 8. So number 8 says Fig 8.1 shows nitrogen and oxygen are being obtained from air. So we have air, and then dust filter, and then we're going to have a component Q removed, component R, and then compression, and then we're going to have components compressed and allowed to expand, and then liquidification, process P, which is the fractional distillation, and then we're going to have nitrogen and then oxygen here. So the question says state the conditions required to obtain liquid components, right? State the conditions required to obtain liquid components. So we want to just to break down this liquidification of air. So first, air is filtered to remove dust, and then we are going to have water vapor and carbon dioxide. So this one is the water vapor removed, and then this one is the carbon dioxide. So they must be removed to prevent a freezing and a blockage, right? So they must be removed. So this one is the carbon dioxide. They must be removed to prevent freezing and blockage, we can occur at the later stages, right? And then we are going to have the compression. So this is the process of compression, right? So we are going to have compression. So the clean and dry air is compressed to high temperatures of about high pressures, of about 200 atmospheres, right? So here we are going to have the cooling and the expansion, right? So the process of cooling, of compressing and the expansion is repeated. So here air becomes liquid. So air becomes liquid, and then here we're having the fractional distillation. We're having the fractional distillation of this liquid air. And then first we are going to obtain so you need to know that nitrogen will boil at minus 196 degrees Celsius, and then we are having argon, which will then boil at minus 186 degrees Celsius, and then we are having oxygen, which will boil at minus 183 degrees Celsius, right? So we are now moving on to the equations. So the first part says state the conditions required to obtain liquid air. So we are going to have low temperature and then high pressure. As simple as that. Low temperature and then high pressure, because we said we are going to have compression here, increasing pressure, right? This is the pressure. And then name the process P. We said it is fractional distillation, and then identify the components Q and R. Here we say it is the water vapor, and then this one it is carbon dioxide. And then we move on to the next part. So the next part says nitrogen and hydrogen react reversibly as shown by the equation. So this is the equation, right? And then this is an exothermic reaction, right? Exothermic reaction, as you can see. And then state the industrial importance of this reaction. So we are going to produce ammonia, so you should be able to give the uses of ammonia. So ammonia is used in the manufacturing of fertilizers and explosive and other chemicals, right? Explosive and other chemicals, right? And then describe in terms of chemical equilibria So whenever you hear this term chemical equilibrium, always remember of the Le Chatelier's principle. Always remember of the Le Chatelier's principle. So your answer should include according to Le Chatelier's principle. There is no other way you can explain equilibrium leaving out the Le Chatelier's principle. Your answer should include the term according to Le Chatelier's principle. This is going to do this, right? Your answer should always include that Le Chatelier's principle. So describe in terms of chemical equilibrium the effect of increasing pressure. So when we are to increase pressure on this reaction, we are going to favor the direction of the reaction where we are having fewer number of moles. So here we are having 1 plus 3, we are going to have 4, and then here we are going to have 2. So increase in pressure will favor this forward reaction where we are having fewer number of moles, right? So here for this reaction we use a pressure of 200 atms, about 200 atms, right? So we said according to Le Chatelier's principle, increase in pressure will favor the direction where we are having fewer number of moles, thereby increasing the number of moles there. So we can say this one will favor the forward reaction where we are having fewer number of moles, right? Thereby increasing ammonia yield. And then the temperature, increasing the temperature. So this one is an exothermic reaction. So if we were to increase temperature, we're going to favor this endothermic direction. So increasing temperature will favor the backward reaction, thereby reducing the amount or the yield of ammonia, right? We are saying that increase in temperature will favor the endothermic reaction, the backward reaction, we can say the backward reaction, thereby reducing the yield of ammonia. So your opening statement is, it must be according to Le Chatelier's increase in temperature, according to Le Chatelier's increase in pressure, according to Le Chatelier's. Your opening statement must always include according to Le Chatelier's principle, because it is the only principle which governs chemical equilibrium. Are we together, guys? So this is what you need to understand. This is what you need to understand. And then we proceed to the number C. So number C says table 8.1 shows the volume of a gas produced at 0.5 minute interval when sulfuric acid is added to the lumps of lime. So limestone, it is calcium carbonate. So you are given the reaction between sulfuric acid and limestone. So we said carbonate plus acid, we are going to have salt, which is calcium sulfate, plus carbon dioxide plus water. So you can balance the equation, right? And then we are having lumps. So at times you'll be examining this type of equations in reaction kinetics. So lumps, they've got a reduced surface area. So at times it can be said we are using lumps and then we are also using powdered. So powdered, they've got a high surface area. So the reaction for powdered is faster compared to the reaction for the lumps. So you must take note on that one, right? And then plot the graph of A1, the volume of gas produced against time. So we are simply plotting the volume against time, as simple as that. And then deduce, so you can go, so this is the graph, and then this is the volume here, and then the time interval. So 4 minutes, go straight, and then try to match out the volume that are given interval. And then sketch on the same axis L2 expected if we are to repeat using lower temperature. So for lower temperature, we are going to have the rate of the reaction slower, the production of bubbles at a slower rate. So you're going to have a graph with the reduced steepness, right? As simple as that. So let us say this one is the graph for A1. So this one is going to be the graph for L2. As simple as that. And then we are going on to number 9. So number 9 says magnesium reacts with steam to produce gas A. Magnesium reacts with steam to produce gas A in the white powder, right? So fig 9.1 shows the setup, and then here we are having heat, and then soaked wool, and then magnesium, and then gas A, and then here's the water. Write a balanced chemical equation for the reaction. So we are having magnesium reacting with steam to give magnesium oxide plus hydrogen gas. So you should include the state symbols. Since you are told that it's steam, they want to make sure that you understand that steam is water in the gaseous phase, right? And then describe and explain why gas A is collected by the method shown. So this is what we call the downward displacement method. So this is what we call the downward displacement. Hydrogen is insoluble in water, so we need to obtain hydrogen. We need to collect hydrogen using the downward displacement of water so that we can prevent the mixing of hydrogen with air. So this method allows us to obtain pure hydrogen gas, right? Pure hydrogen gas. And then we move on to the next equation. So number B says, in the extraction of copper 2 sulfide is reduced to copper by heating in a controlled amount of air. The chemical equation for the reaction is shown. So this is the chemical equation for the reaction. We are having copper 2 sulfide plus oxygen to give copper 2 metal plus sulfur dioxide. Alright, so here we are required to calculate the amount of copper 2 sulfide required to produce 320 kgs of copper. Right, so from the equation, 1 mole of copper 2 sulfide will give 2 moles of copper. So we want to convert these quantities to masses, right? So the mass of copper 2 sulfide, we are going to have 64 the AR of copper by 2 plus that one of sulfur 32. So we're going to have 64 by 2, which is 128 plus 32 to give us 160. And then here we're going to have 128 64 by 2, which is equal to 128. So we are saying that 1 is equal to 2. So in other words, 168 grams is equal to 128 grams, right? And then calculate the amount which is required to give 320 of copper. 320 kgs into grams, you can multiply by 1000 to give us 32,000 grams. So here more is equal to 320,000 grams. So we can carry out the simple proportion. So it's 160 grams multiplied by 320,000 divided by 120 grams, right? So we are multiplying this with 32,000 divided by 128, and this will give us grams, 400,000 grams, which can be converted to 400 kgs by dividing by 1000, the mathematical procedures, right? And then the next equation says, describe the effect of sulfur dioxide to the environment and explain how the emission of sulfur dioxide can be controlled. So we are simply going to explain the effect of sulfur dioxide like what we did in the previous question, right? So the effect, it causes acid rain, which can damage the buildings, eroding the buildings and the aquatic environment, and also the forest, and can also affect the respiratory systems, right? Through the inhalation of sulfur dioxide. And then to control, we can use what you call the flue gas desulfurization. So for control, we can use the flue gas desulfurization, or we can use low sulfur fuels, right? Or we can use catalytic converters. So you should understand how the catalytic converters functions, right? So you should understand how the catalytic converters functions, right? So a catalytic converter, it is a device fitted on the cars, fitted to the exhaust system of vehicles to reduce harmful gases produced during the combustion of petrol by burning petrol, diesel, or fuel, right? By burning petrol or fuel, any other fuel, right? So the function is to convert poisonous gases into less harmful gases. So we want to convert poisonous gases into less harmful substances, right? Before they are released into the atmosphere. Are we together? And then we can have the harmful gases. We are having carbon monoxide being oxidized to carbon dioxide. We are having the oxides of nitrogen, nitrogen monoxide, and then nitrogen dioxide reduced to nitrogen gas. And then we can also have soot or unburnt hydrocarbons. So they are oxidized to carbon dioxide and water, right? So the effect of these ones, so this one is very, very poisonous in the body. It forms what you call carboxyhemoglobin, a stable compound which reduces the oxygen concentration within the body, right? It's very, very poisonous, very, very dangerous. And then this one causes acid rain, and then this one contributes to smoke, right? Smoke formation. Are we together? And then the catalyst used, we are having platinum, and then palladium, and then rhodium, right? And then rhodium. So this is what you need to know for the catalytic converters, right? And then we go on to the next equation, to the next equation, right? So number 10 says fig 10.1 shows the chromatogram obtained using different single dyes. We have green, brown, and then purple, and other three substances A, D, E, and F. So this is the filter paper, the solvent paper, and then we are starting here, the starting line. All right. So name two dyes present in D. So here is our D, and then we have these dyes. So we go straight horizontally. So we are having dye purple, and then here we are having the green one. So this is very, very simple, very, 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 very simple. And then identify with the reason the dye that is most absorbed by the filter paper, adsorbents, right? So we normally discuss adsorbents when dealing with chromatography and catalysis, especially the homogeneous catalysis, right? So the one which travels a shorter distance, a shorter distance, adsorbs strongly to the filter paper. So where we are having the shortest distance from the starting line, it is on green. This one has got a larger distance. This one is got a medium. So our correct answer, it is green. Why? Because green travels a smaller distance, meaning to say it is strongly attached to the filter paper. That's adsorbents. Alright, so the next part says name the factors that enables a liquid to be separated by fractional distillation. So fractional distillation, we are separating using the difference in boiling point. So we have types of distillation. We have simple distillation, we have fractional distillation, and we have what you call steam distillation. So you should know these types of distillation. And then name the last fraction that comes out fractionating column when fractionally distilling petroleum. So you should know the order, right? So we are starting with refinery gases. Mainly we have propane and butane. And then we go on to petrol, and then naphtha, and then we go on to kerosene at times called paraffin, right? And then we go on to diesel, at times called gas oil. And then what else? We go on to lubricating oil, and then lastly we are having bitumen, the residue, bitumen. So this is the order. So first we start with refined gases, propane or butane, right? And then name the last fraction. So we say it is bitumen. And then state one use of the bitumen road surface is making road surfaces, right? And then we go on to the last part, number C. So number C says modern cars are fitted with life-saving devices such as airbags, and then the airbag contain an explosive material which is sodium oxide. And then when a vehicle undergoes a head-on collision, high temperatures are generated, causing the chemical to decompose to sodium, metal, and nitrogen gas, which inflicts the airbag. Write a balanced chemical equation. For the reaction that occurs when in the airbag when a collision occurs. So we are having sodium oxide decomposing to give sodium metal plus nitrogen gas. nitrogen gas. So to balance this equation, we are going to need a 3 here, and then we are going to have a 2 there, and then a 2 here, right? So it's now balanced. And then name the type of reaction that occurs in the airbag. So this one is a decomposition reaction. We are decomposing sodium azide to its constituent elements, right? So it is a decomposition reaction. Are we together? An airbag of a car requires 42 cubic decimeters of nitrogen to be inflated. Calculate the mass of sodium azide needed to fill the airbag at RTP. So at RTP, so we are given the volume. So the volume is 42 cubic decimeters, and then at RTP, 1 mole is equal to 28. So we want to calculate the number of moles here is equal to 28. So we are saying 1 mole is equal to 28. What about 42? So 42 will give us more. So we are saying 42 over 20 over 28. So it's RTP for Zimsec, we say it is 28, right? So you must take note of that. So it's 42 divided by 28. And then we are going to have 1.5 moles, right? We're going to have 1.5 moles of nitrogen. So we go back to the equation. When we are having 2 moles of sodium azide, we are having 3 moles of nitrogen, right? So we must use the molecular ratios. So 2 is equal to 3, right? And then less is equal to 1.5. So we calculate the number of moles for sodium azide. So 1.5 over 3 by 2. So 1.5 divided by 3 multiplied by 2. This will give us 1 mole, right? This will give us 1 mole. So the mass of 1 mole of sodium azide, so N is equal to mass, right? So N by MR will give us the mass. So the molecular mass for sodium azide, so N, so 23 plus 14 by 3. So 14 by 3 will give us 42 plus 23, and this will give us 65. This will give us 65 grams, and we are done.